Hi guys, and welcome to this lecture on RC time constants. This one is, I think it's a little bit interesting. We're now going to have a look at some capacitors like this little guy, and another one that I've got connected in a circuit over there. And we're going to have a look at what happens when you combine it with a resistor in a circuit, and we're going to look at it practically as well. I've got a multimeter there, so it should be a little bit of fun. Okay, so first, let's have a look at this page. So this has got quite a lot of content in here, and it's designed so you guys can download this as a PDF and help you along with your own little experiments. So have a look at the circuit first. I've got voltage applied over here, 10 volts. So I've set my power supply to 10 volts, and as we'll have a look at in a second, or in a few seconds, we'll have a look at the circuit I've built over here, which is exactly the same as what we're seeing. So 10 volt power supply, a 1 microfarad capacitor, in series with a 1 k ohm resistor, and then we have two switches over here. The switches I'm using are little buttons, so when you push the button it closes the circuit, so we have a complete circuit like this. That would be closed over there, and when it's not pressed it's open. So two switches. This one is my charge switch, this one is my discharge switch. Now we'll have a look, we'll come back to that in a second. I've got the circuit over there, but what I want you to have a look at over here is this universal time constant chart. So I've drawn this one up. If you type that into Google, you'll find very similar things. And I've rounded off my percentages a little bit, which is going to be fine for what we're doing here. Now, so what I've got here is I've got the vertical axis, so that's the one going up this way, and this is what we call amplitude. Now I've got two different amplitudes represented here. You'll notice I've got the green one coming down there. That represents current in the circuit, as in the current flowing through here. And then the red line indicates voltage, which indicates the voltage across the capacitor there. Now let's have a look at these black lines I've got going here. So I've got, I've got 1T, 2T, 3T, 4T, 5T. So each one of these represents a certain amount of time, and they're broken up into what's called time constants. So see, it's called the universal time constant chart, so there's the word constant in there. Now a time constant is something we're going to use in our capacitor resistor circuits, and later on when we get to our inductor resistor circuits. But we do a little bit of a calculation to figure out how long is one time constant. Once we've figured out how long one time constant is, we can work out how long it'll take to charge the capacitor, because it takes a full 5 time constants to do that. Now, let's come down here for a second, then we'll go back to the chart. Let's just get a bigger, here we go, fat plus, and let's go red. So if we have a look here, I've got a bit of a formula, and I've done a complete calculation for you. So one time constant is given the special letter T. I just draw my T's like that, but there's other, I think it's like a special T like that, in fact. Now that there is one time constant. That's the letter that we give it. It's a really simple calculation. It's just the resistance multiplied by the capacitance. So check out up here, we've got a resistor of 1 k ohm, 1000 ohms, and a capacitor of 1 microfarad. So we do 1 k ohm multiplied by 1 microfarad, and that gives us 1 millisecond, because the answer is in seconds. In fact, if we were to do it on the calculator, which I will do, so we've got 1000 ohms multiplied by 1, micro, so times 10 to the negative 6, we get 1 times 10 to the negative 3. So 1 times 10 to the negative 3 is 1 milli, and it's in seconds. So what it's saying is, from when I first close this switch, when the capacitor is completely discharged, it's got 0 volts across it, when I first push that button to close that switch, I'm going to have electrons traveling through here up to here. And it's going to start filling in electrons on that bottom plate. So now there's going to be more electrons than protons, so it's going to start to become negative. At the same time, on the top plate, you're going to have all the electrons being attracted away from there, going to the positive of the power supply. Now that the electrons are leaving there, there's going to be more protons than electrons, therefore it's going to become more positive. Now, after 1 millisecond, which is 1 time constant, so there it is, 1 time constant is 1 millisecond, the voltage is going to go from 0 volts all the way up to 63% of the total. What is the total? Well, the total is 10 volts. So let's figure it out. What's 63% of 10 volts? Let's do 10 multiplied by 0.63 to get our 63%. It should be at 6.3 volts after 1 millisecond. Alright, well what if we wait another 1 millisecond? So I've pressed the button, these electrons are still flowing onto this guy and electrons are flowing away from this guy. So this is going even more positive and this is going even more negative with respect to each other. So after the next 1 millisecond, after the next time constant, this continues to go up and we're now at 86%. What's 86% of 10 volts? Well, 10 times 0.86 is 8.6 volts. And then after another 1 millisecond, we're going to be at 9.5 volts. And after another 1 millisecond, we'll be at 9.8 volts. And then finally, after the next 1 millisecond to give me a total of 5 milliseconds, we're at 10 volts. Now these are approximate. It's around about 63%, around about 86%, around about 95, 98, and 100. But it's really, really, really close to what the actual values would be anyway. So it's perfectly fine for what we're doing. Let me get rid of all of this now. Okay, so let's have a bit of a think. Why does it take, so when we start off, this thing is 0 volts. It's completely discharged. When we first press that button to close the switch, why does it charge really quick to begin with and then slow down as time goes on? Why does that happen? Well, let's have a think about it. Remember how we dealt with voltage dividers in the past? So let me just get a thin marker here. That's where we had a simple series circuit of 1 resistor and 2 resistors. If that was 1K, that was 1K, and this was 10 volts, they'd each get 5 volts. Well, we're doing pretty much exactly the same thing, except instead of using 2 resistors, we're now using 1 resistor and a capacitor. So if this capacitor has 0 volts across it, and then we have a switch here and we close that switch, the capacitor takes time to charge, so it's still going to have 0 volts across it when we first close that switch. Therefore, where does all that 10 volts show up? Well, it shows up across this guy. This has 10, this has 0. 0 plus 10 gives you 10. Let's get rid of all that. Ugh. Come on. So it's a voltage divider, which means we're sharing the full 10 volts between this one and this one. If the capacitor had 0 volts on it when we began, when we first pressed that button to close the switch, it's going to have 0 volts on it from that very first instance. So therefore, let's just get rid of this. Okay, there we go. Let's first close the switch. This was discharged. It has 0 volts on it. But what about this one? Well, this would have to have 10 because we have to share that 10 between that and that. 10 plus 0 is 10. Let's work out the current in that case. So current equals 10 volts, which is the voltage across the resistor divided by the resistance. That is 10 milliamps. So when we first press that button, because there's 0 volts across there, this gets the full 10. Therefore, the current is going to be way up here at 10 milliamps. So that's 100% of what the current could ever possibly be. Okay, but now that we do have current flowing in the circuit, actually, let's put those back, there we go. Now that we do have current flowing in the circuit, that means electrons are going to start building up over here and starting to go a little bit negative. At the same time, electrons are leaving the top plate. In their place, there's going to be way more holes than electrons, so it's going to start to go a bit negative. So if we're now starting to get a little bit of a difference in potential between the bottom plate and the top plate, we're no longer at 0 volts anymore. So let's say that after a period of time, we get 1 volt across here. This plus this must equal this. If that capacitor now has 1, what must this have now? 9. So after a certain period of time, with the electrons starting to move around, build up on the bottom plate and leave the top plate, we're starting to get a negative positive thing happening. Therefore, this starts to take on a voltage, and this one up here gets less. So therefore, the current instead of being 10 milliamps, is now going to be 9 volts divided by 1K equals 9 milliamps. So the current is now less. So you can see the current is actually dropping down here while the voltage across the capacitor goes up. Okay, therefore we get more electrons building up down the bottom plate and more electrons leaving the top plate going to the positive of the power supply. So this gets even more positive and even more negative with respect to each other. So this goes to 2 volts. If that's got 2, this must now have 8, because this plus this must equal 10. What's happening to the current? Well, we now have 8 volts divided by 1K equals 8 milliamps. So we started at 10. That caused this thing to charge because we need electrons to start to flow to and from the plates for that to happen. As its voltage goes up, the current keeps coming down because we're leaving less voltage for this resistor. The way we work out current is the voltage across the resistor divided by the resistor. So you can see that we keep coming down and down and down and down and down with the current as the voltage across this guy goes up and up and up and up. But my question was, why does it actually taper off? Well, the reason it tapers off is because when we first closed the switch, and this had 0 volts across it, oh, that's a really bad 0, all of the voltage, so the full 10 volts, was across the resistor. So if the full 10 volts is across the resistor, that is where, oh dear, come on, you can do this. That's where we're going to have the most amount of current flowing the circuit, 10 volts. 0 volts. From there, it means that we can start to charge the capacitor really quickly. If it's charging quickly, its voltage goes up really quickly. But the problem with that is, if it gets more voltage, it leaves less for the resistor. If there's less on the resistor, there's less current. Eventually, we finally get to 10 volts across here. If there's 10 volts there, how much can be left across the resistor? Well, this plus this must equal this. Therefore, there's 0 volts across the resistor. 0 volts divided by 1K, well, you're going to get 0 amps. There is no current anymore once this thing is charged. How long does that take? It takes 5 time constants. How long is one time constant? Well, it's 1K times 1 microfarad, 1 millisecond. So finally, to get fully charged, it takes 5 of those. So 5 times 1 millisecond is 5 milliseconds. Wow, that was quite a mouthful. But hopefully some of that stuff sunk in then. Okay, I was going to delete that, but that's okay. Now what about discharging? If we were to close, if this was charged, 10 volts, and we were to leave this switch open, and now we close this switch, what's going to happen there? Well, remember when this thing charged, we had negative and positive showing up like that. So the electrons, once we close this switch, the electrons are now going to flow through here, up through that closed switch, through the 1K resistor, down here to the positive. As that happens, we're now, because we're pouring electrons over to here, this is going to become less positive compared to here. Eventually it's going to get all the way down to where the top and bottom plates have exactly the same number of protons as electrons as each other. Therefore there's therefore there is 0 volts difference between them because they're at a point of equilibrium. There is no difference. I'm just checking, keeping an eye on the time there. Okay, so what's going on with this curve? Why is there only one curve? Why don't we have another one going up this way? Well, the reason for that is the capacitor is now acting as the power supply for this circuit. So if the power supply is decreasing, the current must also decrease. So notice that the voltage and the current are following exactly the same line. They're both starting up at maximum and then going down and down and down and down and down to nothing. How long is this going to take? Well, from being fully charged to fully discharged in this circuit, from 10 volts to 0 volts, it's going to take 5 time constants. How long is one time constant? Well, it's the same as before. Resistance times capacitance, 1K ohm times 1 microfarad is 1 millisecond. 5 times 1 millisecond equals 5 milliseconds, exactly the same as what we were looking at when it was charging. It's going to take exactly the same amount of time because the components have not changed. So when I connect that switch, the electrons travel through here all the way up around to the positive. After 1 millisecond, we will have dropped down by 63%, which means we'll now be down to 37% of the total. So we're going to be up here at 10 volts, and we're going to go all the way down by 63%, which means now we're sitting at 37% of the total. And then we're going to drop down after the next 1 millisecond. We're going to drop down by 80. Ooh, did I get that wrong? Why is that? Oh, there we go. It's going to drop down by 86%. So now we're sitting at 14%. And then after the next 1 millisecond, we've dropped down by 95%. So we're sitting at 5%. So after 4 milliseconds, we've dropped down by 98%. We're sitting at 2%. And then finally, after the full 5 milliseconds has taken place, we're sitting down at 0 volts, 0%. All right, so that's that. Let's see how quickly we can do this. So I want to show you these circuits practically using a multimeter net over here. So I'm going to move my light and myself over here. Turn on the multimeter. I'm going to set the range just so it's a little bit easier to read. So as you can see, power supply is connected here and here, positive, negative, and it's 10 volts. I've got my 2 multimeter leads connected through these other wires just to allow my hands to be a bit free to do other things. 1 microfarad capacitor and a 1K resistor. This is my charge button and my discharge button. So let's have a look at the charge across the capacitor. It is 0 volts, which it should be. Now when I press this charge button, after 1 millisecond, so if you follow this along, after 1 millisecond it should be up at 6.3 volts. And then after 2 milliseconds it should be at 8.6 volts, and just keep following its way along until we get to 10. But notice how it's going to take 5 milliseconds to get the total, which is 10 volts. So it's going to be basically an instant thing. I press this and have a look at what happens here. So pretty much instantly it went to 10 volts. What about discharging? So instantly 0 volts. An instant charge, instant discharge. So really quick. But what if we want to actually see this change? So let's have a look at this guy. Let's get rid of the 1 microfarad capacitor and the 1K resistor. I'm going to get a 10K resistor there. Connect that back to my discharge switch. And look at this big guy. A 1000 microfarad capacitor. What is one time constant with this? Well, it's 10K times 1000 microfarads is 10 seconds. So after 10 seconds, it'll be at 63%. After another 10, it'll be at 86%, and so forth, and so on. So this time, to get fully charged, we need 50 seconds. So I'm just going to make sure this is discharged by pressing this. I'm going to bring up a clock, which I thought I had open, but obviously not. Alright, let's have a look. I'm going to charge when the blue hand gets to the 4. And we're just going to follow this along. Okay, so after 10 seconds, we should be up here at 63%, which is 6.3 volts. Which was kind of close, but a little bit off. So after the next 10 seconds, we should be at 86%, which is about 8.6 volts. Pretty close. Let's see, after the next 10 seconds, we should be at 9.5 volts, 95%. Again, pretty close. After the next 10 seconds, we should be at 98%, or 9.8 volts. Ooh, that one was very close. And then finally, this is getting up to our 50 seconds. We should be up here at our 100%, which is about 10 volts, which is there. So very close. If I was to discharge this thing, I press the button and it slowly discharges. It'd take the same amount of time, 50 seconds, to completely discharge. And so I won't wait the full time for that, but you can see it's going to do the same thing. So, and you can see it's storing its charge there. I'm not pressing any buttons and it's storing that. Well, my 20 minutes is almost up, so thank you guys for watching. Download the PDF. And then make sure you go and do the questions, because there'll be lots of questions here for you guys to do a few calculations yourselves. Alright, thanks again for watching this one.